Heidi-ho, everybody. Buckeye Monkey here. Now, I got a few requests to make a video explaining how to use maneuver nodes. And you can't really fully explain maneuver nodes without also explaining the Navball, because the two work hand in hand to help get you where you want to go. This series is kind of intended for the beginner, but not the total noob. Maybe you understand some of the controls, you can get to orbit, but you don't necessarily understand the maneuver nodes, and you're having trouble getting to the moon or some other planets. So first I'm going to throw some ivory tower theory at you. Then I'm going to show you how that theory applies to the Navball and Maneuver nodes. And in parts 2, 3, and 4, I am going to take all of this theory and put it into practical application in game and show you how to do things like land on the moon, get to another planet, and do orbital rendezvous. Now, one of the most important fundamental concepts in Kerbal Space Program is the concept of velocity. Now, some people may think that velocity is just another word for speed, but it's actually a lot more than that. Velocity does include speed, but it also includes direction. So if I tell you that I'm moving at 10 meters per second, I've just told you my speed. But if I tell you that I'm moving at 10 meters per second to the north, I've just told you my velocity. Some of you may be wondering why I've been showing you this footage of this hovercraft-style vehicle that I've been flying around here so far. You know, maybe not technically a hovercraft, it's more of a VTOL, vertical takeoff landing vehicle, but we're kind of flying it around close to the surface here, sort of like a hovercraft does. And really with the stock parts, this is about as close as you can get. The reason is we are going to use a hovercraft in a 2D analogy to explain the concepts of velocity and how it applies to Kerbal Space Program. A hovercraft is a pretty good analogy for a spaceship, except that it works pretty much in 2 dimensions instead of 3. You know, you're kind of sliding around on the surface in a hovercraft, but it is a pretty frictionless vehicle, so it's going to want to keep going in the direction that it's already headed. So how do we represent velocities in a graphical manner? Well, one way to do it is using vectors, which are really just arrows plotted on a chart like this one I've got here. You can see we've got our 4 basic directions, northeast, south, and west. And for this graph, we're going to say that our grid lines here each represent 1 meter per second. So let's say we're in our hovercraft and we are traveling east at 4 meters per second. Well, how do we represent that on this graph? It's actually quite simple. We just start at our origin and we draw an arrow in the easterly direction for 4 units, and there we go. That is our vector. That is our velocity. 4 meters per second to the east. Now, let's say we're in our hovercraft. We're traveling 4 meters per second to the east, and we point our hovercraft east in the same direction we're traveling, and we give ourselves a little thrust, enough for 2 meters per second. Now, this little blue arrow here represents the vector, the velocity that we just added to our current velocity. You know, we were pointing east, we gave ourselves enough thrust for 2 meters per second. But how does that relate to the original 4 meters per second east that we were already going? How do we add those two things together to figure out what our new total velocity is? It's actually quite simple. We start with our 4 meters per second to the east velocity vector. Then we go to the tip of that arrow and add on our new vector. So now, how do we draw a new vector which represents both of these vectors added together? Once again, quite simple. We find where our original vector started, and then find where our last vector ends, and we draw a new arrow from the start to finish. Voila! This is our new velocity vector. We started off already heading 4 meters per second to the east. Then we pointed easterly and gave ourselves some thrust for 2 more meters per second. And funnily enough, that ends up with a new vector of 6 meters per second to the east. Now, this method of adding velocities to each other, adding vector arrows to each other, works in any direction with any combination of arrows. So let's say, once again, we're in our hovercraft and we're heading 4 meters per second to the east. But this time, we're going to point our hovercraft north and give ourselves enough thrust good for 3 meters per second. As you can see, once again, we just keep lining up these arrows tip to tail. We use the same method as before to find out what our resulting new total velocity is by starting at the beginning of our original arrow and then finding the end of our last arrow and drawing a new arrow between those 2 points. Now, I know from some rules about triangles that our new resulting velocity is 5 meters per second at about 37 degrees to the northeast. And one of the really cool things about this method is it doesn't just work for adding 2 arrows together, for adding 2 velocities together. We can keep pointing our hovercraft in all sorts of crazy different directions and giving ourselves various different amounts of thrust. And as long as we just keep adding up our new vectors tip to tail in the same manner, then once we're done with all of our rambunctious steering, we can just follow the exact same rule to find what our resulting velocity from all this craziness is. All we do is find the beginning of our original vector, then find the end of our last vector, and draw a new arrow from the beginning to the end. So all that willy-nilly craziness boils down to just this one simple velocity vector. And I know from a little bit of trigonometry that we're not going to get into right now that this vector is about 8.25 meters per second and about 14 degrees west-northwest. So why did I bore and confuse you with all this gobbledygook about velocities and vectors and hovercrafts and this graph? It's because while a graph like this does a pretty good job of representing our velocities for our little hovercraft example, the hovercraft is mostly moving around on the surface of the Earth, pretty much in just 2 dimensions. Where a graph like this breaks down is it's really hard to represent your velocity in 3 dimensions like you will have in a spaceship. Space is decidedly 3-dimensional, and you have to worry about up and down, as well as all your side-to-side movement. So that is what your Navball is at its core. It is a 3-dimensional version of this graph. It is no accident that I picked the color yellow for my starting vector to represent our original velocity in all of my scenarios. This yellow marker here on your Navball represents your current direction of travel. And in conjunction with this speed indicator at the top of your Navball, you have your direction and your current speed, so you have your current velocity. And a funny thing happens when you go ahead and set up a maneuver node. Once again, it was no accident that I chose blue as the color of the vector arrow that we always added to our original yellow vector. This blue marker on your Navball represents the direction of the vector that you set up in your maneuver node. And coupled with this speed indicator, we once again have speed and direction, or another velocity. Now, you might hear people use the term delta V here and there while playing the game. I'd use it myself. Delta is the Greek letter D, and it is used in math to indicate change. The V is short for velocity. So delta V means change in velocity. And our blue vector, our blue marker on the Navball combined with that speed, represents the change in velocity that we need to affect in order to get our current velocity into our desired velocity. And, since I did not pick the colors of these arrows arbitrarily, you may notice that our desired velocity arrow here is orange. And when you get in game and set up maneuver nodes, you will notice that the expected new orbit as the result of following your maneuver node is a orange dotted line. So hopefully I didn't frighten and confuse you too much with all that theory and gobbledygook about vector arrows, but now let's jump in game and show you how this all applies. So our orange reticle in the middle of the navball represents where our ship is currently pointing. And as we pointed out before, this yellow marker here indicates our current direction of travel. If we were to point at it like we are now and give ourselves some thrust, we would be increasing our speed in exactly the direction that we are already going. So if we swing around to the other side, we have this other yellow marker with an X through it. This marker is always on the exact opposite side of the ball from your direction of travel marker or prograde marker. This one is often referred to as the retrograde marker, and it indicates the direction exactly backwards from your current direction of travel. If we were to aim at this marker and give ourselves some thrust, we wouldn't be changing our direction at all. We would simply be slowing down. And as I give myself a little bit of thrust here, our speed starts going down. So let's swing back around to that prograde marker. It indicates our direction of travel. And give ourselves a little bit of thrust if we can get on that marker there. There we go. And our speed starts going right back up again. And, you know, these direction markers are great and all, but directions are fairly meaningless unless you know the point of origin, and unless you know what those directions are oriented to. You know, if I tell you that my coffee is sitting on the left-hand side of my desk, I've given you a direction. But if you have no idea where my desk is or which direction I'm facing, then the information I just gave you is pretty meaningless. The answer here is that the navball always orients itself according to the celestial body whose sphere of influence we are currently occupying. So right now we are in Kerbin's sphere of influence, so it is orienting itself according to Kerbin. If we were out in interplanetary space, orbiting around the sun, it would be orienting itself according to the sun. And if we got ourselves in an encounter with the moon, Minmus, or one of the other planets, or one of the other moons out there, then it would be orienting itself according to whichever moon or planet we are currently near. So if I point ourselves right up at the dot on the top of the blue side of the navball, that represents up. And as you can see, my ship is pointing directly away from Kerbin at this point. And if we swing on around to the dot at the bottom of the navball in the orange area, then we are pointing directly at Kerbin. We're pointing down. But the navball isn't just good for up and down. Along one side, we've got this orange line marked with an N, and guess what? That N stands for north. And depending on what kind of orbit you are in, true north could be found anywhere along that line. We are in a rather equatorial orbit around Kerbin, so true north is right along this horizon line where the horizon line and the orange line intersect. And if we swing along this horizon line and follow it around to the opposite side of the navball to the 180-degree line, then we will be facing south. Once again, we are in an equatorial orbit, so south is pretty much right on the intersection between the 180-degree line and the horizon line, between the blue and orange sections. But south is always found along that 180-degree line. If we move on up to the 90-degree line, right around where our prograde marker is, you'll see we are facing east. We are in a easterly orbit. And swinging right around to the other side of the ball to the 270 line, right where our retrograde marker is, we are now facing west. So, there you have it. Up, down, north, east, south, and west. The navball always shows you where your ship is pointing in relation to, in this case, Kerbin. Here I've put myself in a highly inclined orbit, so you can see what I was talking about earlier. If I point at the horizon and the north line, at this point, because I'm like 45 degrees away from the equator, I'm not really pointing true north. So I need to come all the way up here to this 45 degree line at the intersection of that in the north line. And now I'm pointed, pretty much parallel with the poles of Kerbin. Now I'm pretty much pointed north. This is just one of the many reasons why it's generally a good idea to stick to equatorial orbits around whatever you are orbiting, because in other orbits the directions get a little bit harder to understand. Now, the Navball actually has 3 different modes that you can cycle through by clicking on the velocity at the top of the Navball. Right now we are in orbit mode, so it is showing our velocity and direction in relation to the planet Kerbin to some arbitrary point in its center without taking its rotation into account. But if we click and switch ourselves to surface mode, it gives us our direction and speed in relation to the surface of the planet below us. Now that's useful when you're trying to land on something like a moon with no atmosphere and you need to use your rockets to burn. You need to take the rotation into account and need to know how fast you're moving in relation to the surface. There is also a target mode that we will mostly get into in part 4 about orbital rendezvous. That's really where it comes into play the most. But let's switch ourselves back to orbit because we are not trying to land on Kerbin, and Kerbin has an atmosphere anyway, so we can just land using parachutes. We don't really need to use the rocket and be precise with it. Also, the game will automatically switch you between orbit and surface mode, depending on how close you are to the planet. When you start on the launch pad in Kerbin, you are in surface mode, and when you take off and get up around to the edge of the atmosphere, it will automatically switch you from surface to orbit. And when you get in close to some moon or other planet, it'll switch you back from orbit to surface. And yeah, so that is the Navball. There's a little more to it, especially when you set up maneuver nodes or select targets, but we are about to get into that. So here we are in orbit, and this bluish circle here around Kerbin represents our current orbit. There's a couple markers on here. One is the apoapsis, the other one is the periapsis. And these two places represent our furthest point away from Kerbin, which is the apoapsis, and our closest point in our orbit to Kerbin, which is the periapsis. Depending on what we're doing, these 2 points are typically the most fuel efficient to make changes to our orbit. And they also give us a great indication of how circular our orbit is. If they're both about the same distance from Kerbin, that means we're in a near perfect circle. But there's some situations where getting in a really long stretched out oval is advantageous for what you want to do. So let's go ahead and create a maneuver node. We do that by clicking on our orbit at some point and clicking on that Add Maneuver button. And this will give us 6 handles we can pull on. The first one should be recognizable. It looks just like your prograde marker. It represents burning in the direction of your prograde marker. And what that will do is speed you up. And whenever you speed up, it's going to push out the opposite side of your orbit. Now if we pull on the retrograde handle here, which represents burning in the retrograde marker, that's going to slow us down. And that has the opposite effect. It pulls in the opposite side of your orbit. You can set up multiple maneuver nodes in a row if you want. I have not executed that first maneuver node yet, but I can set up a resulting maneuver node based upon where that first one is expected to get me. And as you can see, the same thing, if I pull on that prograde marker there, it represents speeding up at that point in my orbit, and it will push out the opposite side of the orbit. And, if we pull on the retrograde handle, once again, that represents burning in the direction of a retrograde marker on our Navball, and that slows us down, which has the effect of pulling in the opposite side of the orbit. Let's get that back out to about a circle there. The prograde and retrograde handles represent the most fuel-efficient way to change your orbit, because all you're really doing is stretching it around. The other handles will kind of move your orbit in its entirety, and that can be expensive fuel-wise. The blue markers, this one represents burning straight at Kerbin, and as you can see, it kind of shifts our entire orbit around back to the left there, if we consider ourselves facing forward on the prograde marker, it also stretches it out a little bit. Now, the blue handle represents burning straight away from Kerbin, and it has the opposite effect. It'll push our entire orbit in the other direction, and it'll end up stretching it out a little bit too. You know, all of these handles, except for the retrograde one, will speed us up in some fashion in our orbit, and that's why they all end up pushing out that apoapsis. And these last two handles, the purplish triangles, are the inclination handles. What they will do is tilt your orbit up or down around your maneuver node. So pulling on the one handle, burning north, will tilt our orbit in one direction, but it's also going to stretch it out a little bit too. And pulling on the other handle, the south one, will do the exact opposite. It'll tilt us the other direction. And once again, it's going to warp the orbit a little bit as well. You know, see there, it pushes out our apoapsis quite a bit. So because anything you do will warp your orbit in some way like that, you're typically going to have to pull on, 2 or 3 or all of these handles in order to get your orbit into exactly what you want it to be. And once again, when we set up a maneuver node like this, it is going to create a blue marker on our navball, and it's going to put a speed meter off to the right-hand side of our navball. And those two things represent the change in velocity that we need to affect in order to get our current velocity into our desired velocity, and that will translate our current orbit into our desired orbit. Well, there you go. The navball and maneuver nodes explained, as promised. And in the next part, we are going to show you how to use all of these concepts in order to get yourself to the moon, land on the moon, and get back safely to Kerbin. You know, I could have just ditched all the theory and shown you the steps you need to take to get to the moon. But that wouldn't really teach you the deep knowledge that you need to know in order to invent your own missions and go other places, other planets, maybe in a giant series of steps. And since we did cover these fundamentals, my hope is that by the end of the series, you'll be able to make burns and make adjustments to your orbit or your trajectory without even setting up a maneuver node sometimes, and I'll demonstrate how to do that in some of these upcoming parts. You know, the maneuver nodes are nice, but sometimes they can be a hassle, and sometimes they just aren't needed if you understand what the navball is telling you. Thanks everybody for watching. If part 2 isn't already up on YouTube, it should be within just a few days here. So please hit that subscribe button if you're looking forward to it, and you'll be able to find it nice and easy. In the meantime, maybe throw a Kerbal or two in the path of a rocket engine and see what happens. You know, for science.